Good morning to all of you. I myself, Swarup Mahapatra, and just previous lecture was somewhat on combustion, that is chemical thermodynamics. As we understand that if the thermodynamics happens to be the guideline, and next part comes to the heat transfer, which is the reality. And here this particular lecture is targeted to address that of a conjugate heat transfer within a differentially heated enclosure. And the point of saying is that how to establish some of the axioms, some of the philosophies, so that we can just bring this particular philosophy to industry. So before going to industry, we need to do some homework over here and how to make it a very solid and consolidated one, so that everyone can understand and believe and trust, and which will be at the end of it, the results will be somewhat fruitful and which will be meaningful. So with this, this particular one more or less I will be focusing on that of the different equations that governs and how these equations have been taken care of, ultimately what we are going to do with those equations, and how these results, whatever the numerical modeling we will be doing, and how to believe these results, that is what, and that becomes the, ultimately it is given to you or commercially available as softwares. And whether they are black box, whatever you are putting something inside, some result will be coming out. Should you believe that? And under what condition should I believe? Then some experimentation should be conducted, and if experimental results and numerical results they are saying the same thing, possibly we will believe the results. Okay, that is what is the objective of this particular lecture. This is what just I am giving some slides. This is well pertaining to this particular course, fire dynamics and safety. Here it is a how the fire spreads in a particular building, in particular environment, and what makes it to spread. Now the question comes, within what time frame it will be burning some this much of area. You might be hearing some of the things, that is in some of the jungles it spreads and then it goes to one hill to another hill. What in between they used to create, they understand that within what time it will be spreading, and they create a in between some of the, they clean out some of the trees so that it will not go jump from one hill to the other one. So these are all, even if day to day it is going on, but can we make it some deterministic way? What is the exact time frame so that we can predict? That's the real challenge, whatever we are having and at present day. So these are ultimately what happens, what it specs. Can we think of the temperature field? Can we think of the velocity field? How the combustion is going on? All these things, if we can really predict, then all that of your fire spreading time, temperature, devastation, all these things can be predictable and determinable. So these are some of the patterns, and similarly flow pattern around a plane, and that is obstacles in a free stream flow. This is two cylinders in a cross stream, and flow pattern inside a pump, and this is pressure variation around a moving truck, and these are flow around the backfilled container, and this is the flow patterns in a data center. So even if the flow thoughts in human height, that can be thought of and they can be modeled, and we can think of how this flow pattern can be modeled. So this is center is nothing but your computational fluid dynamics, which speaks about that of a fluid flow and its dynamics, kinetics and kinematics, and using the support of that of a computer and a tool. And this is well known what the fluid is. When we talk the fluid, we understand that of air, water, corrosion and all these things, and we will take that of a mathematical platform, that is nothing but property, density, conductivity, all these things are coming as a definition of the fluid. And similarly, we know that of a dynamics, so dynamics is nothing but that of what is the force involved in, what is the cause and effect that is coming into picture, and what are the forces that are coming, what are the opposing forces that are coming. So all these things you say now, ultimately what happens, force is equal to mass and acceleration, so that is your Newton's second law. And this, all this ultimately what we want to have it, that of your dependent variables should be treated as a function of that of your independent variable. Can we just a functional relationship between dependent variables and independent variables, and that is with the support of a computer which is meant for computing and that of storing and all these things. So friends, so any phenomena you think of, any phenomena, it has having its physics. So physics needs to be transported into your mathematics, and this mathematics is nothing but set of equations and governing equations, and they are being developed with using some of the conservation principles, basic physics of it. And ultimately what we need to predict is dependent variables should be a function of that of your independent variable. Y is equals to f of x. So x are the independent variables, y is the dependent variable. Can we just come up with this similar sort of relation? So that is what is the fundamental one, and that is one of the target. So we understand, and on what we are searching for, analytical solution, numerical solution and experimental solution. So analytical solution is the best one, no doubt about it. But the question is that with whatever the mathematics we are learning, can we really get that of an analytical solution? Is that if all the solutions are available analytically? All this mathematics we are handling, can they be solved? All these equations so far, are there some mathematics and their solution schemes are really available to us? So many questions are there. So in absence of those, and in the problems which are nonlinear problems, and normally engineers they grapple that of a nonlinear problems. So, and the day-to-day life we are thinking of, it's a nonlinear phenomenon. Human behavior itself is a nonlinear behavior. I mean, chaotic, that is stock dynamics is a nonlinear thing. So anything you take it, that's a nonlinear. And it is to have an analytical solution, absolutely not feasible. Even if Navier-Stokes equation, solving it today is also a challenge. It is $1 million prize is also still ahead of it. Nobody is able to solve it analytically. So what is the left out solution for us? So either you go for some numerical solution or that if you are an experimental solution. Now the question is, should I go for an experimental solution? And without knowing the physics of it, how it will behave, that's also not known to me. So now obviously that is, it lands to, we have to have some of the conceptual understanding of the phenomena. Once we know, then we can think of doing some of the experiment, because around that fact we can conduct some experiments. Then only possibly we can have something. So friends, so numerical solution obviously is one of the things. So I'm just showing some of the mass conservation equation. All of you know, in a differential form this appears. It's a partial differential equation. Similarly, momentum equation is looking like that, is a force balance, and which is nothing but state of that of a partial differential, it's a partial differential equation. And energy equation, which talks about the temperature field it can predict, and momentum equation, it gives you the velocity field. So this energy equation, again it is landing to a partial differential equation. So if you just summarize, either in a, that is pressure variable terms, that is of your all other partial distinct function, these what I wanted to show here it is, they are nothing but partial differential equations for whatever fluid flow problems. So if it is that, and finally what the mathematician club? They club these equations in a very simple form. Either it's a parabolic equation, elliptic equation, hyperbolic equation. It might be applicable for fluid flow. It might be applicable for acoustics, might be that of an electrical field, might be a flow through that of a soil. It can be applicable to anything. Now question is, we need to solve which is appropriate to our field. For a field of combustion where that of a flow is occurring, so fluid flow is a mandatory. So what's that of your equation we are supposed to do, and can we do it, solve it, that is analytical. In absence of that, we need to have this nonlinear system I was talking. So you see, already I told you that is what is the necessary of a numerical technique. when closed form solutions are not available, when analytical solutions are not available, then next question comes experimental. But without knowing the physics, can I solve it? Can I go for experimental solution? Even if you do it, that cost is enormous. You can't just, how to start, how to design it, you don't have any idea about that. That idea needs to be with us. So in order to have some of the physics, some of the solutions we need to have. So therefore, here it is, numerical solution is obviously one of the alternative. Now what numerical solution is all about? I have shown you that if you have the domain and it is discretized. So means an infinite number of points now is represented through a finite number of points. So what is infinite number? Any, if you put it x, any y value, any value, so that becomes analytical solution, you can get it. But instead of doing that, what a domain, we just represent through a finite number of points. So this finite number of points, making that, representing that domain, we call it discretization or that of here. And now what we need, at every point we are searching for the solution. Instead of that, what we will be solving or what we are searching for, those finite points needs to be provided with those variables, such as what you are searching for in a flow field, in a flow phenomena, that is velocity field you are searching, temperature you are searching, concentration you are searching, whether NOx is there or not you are searching, whether carbon dioxide is there or not you are searching. So what is the temperature of the phenomena? So all these things you are searching. So these finite number of points, if they are equipped or they are provided with these values, that is our target and we need to obtain this. Okay? So this is what is the target of the numerical solution. Any governing equations, just now I have shown here through partial differential equations. So now these needs to be solved and these variables should be obtained. What is these variables at these points? Once these points are provided with these variables, certainly in between any point, A and B, 2 points are there, in between another point is there, you interpolate and get some result. That is what is our objective. Okay? So now taking of this, I am not just going, so many methods are there, numerical schemes, I am not just going much of mathematics into it, so that once mathematics will be taught much, I mean at the end of the class nobody will be here. So I will be loving to avoid much of the mathematics. Now I will be taking you to some of the, how you just in the laboratory scale, in the academia, or that of before a technology goes to the industry, how we take it up and we validate, authenticate, and it should be made reliable for the users. That is what is the basic objective. So now here I am taking a problem that is a differential heated enclosure which we understand, we can discuss and debate, and thereafter we will just add on one by one, so that what is the effect of the additional phenomena. For example, I started with the natural convection and its experimental study. Thereafter I am putting some of the radiation effect, and radiation effect is to be isolated, should be understood, and because in combustion radiation is a significant parameter. Once energy equation is solved, you are given with the temperature. Just now Professor Shah was talking of adiabatic flame temperature, because temperature itself, it decides what will be the composition also, right? So these are the things, and an energy equation needs to be solved also. For now coming to this particular small problem which I have taken just for understanding, for a discussion. This is a differentially heated enclosure. Left hand side of it is a hot well, right hand side is a cold well, means temperature you can say that of a 100 degree and the right hand side is 50 degree. So there is a 50 degree variation at temperature difference, and two horizontal walls, let it they be adiabatic. What happens? Once they are all at same temperature, there was no movement, and once left hand side becomes hot or you have heated it, the air which is in contact with that of a hot well immediately start getting heated up and moves up because of the buoyancy effect. So what happens? It expands and raises up because of the buoyancy, but it is now obstructed by that of a horizontal adiabatic corridor. It moves to the right, and right hand side we do have a cold one where it is again condensed, not condenses exactly, it gets cooled down and shrinks. As a result of which, when it shrinks, what happens? The volume reduces, it creates a negative pressure, therefore it shorts that. So now what happens? One side it is getting heated up, expanded, on the other side it is cooled and compressed, and this cycle moves. Okay, this air inside it moves. What does it mean? It means that if you just now go to Carnot cycle, what happens? There is a source, there is a sink, and once the engine is operating in between, and from the source it takes the heat, and the sink, some of it is rejects and some of it is converted into work. So here, similarly on the left hand side, I do have a hot well which behaves as a source, and that the right hand side is a cold one where it behaves as a sink, and in between an engine operates, so which delivers certain amount of work, but that work, where it goes, that work is spent in moving the fluid. The fluid in between moves. For the movement of the fluid, you need some amount of work. That work is coming from this, okay, and that is been spent on moving the fluid. So now if I am just wanting to investigate this particular phenomena, what is my investigation parameters? One is how much of heat can transfer, and where the temperature, what will be the temperature field in between, what will be the velocity field in between. That is what my target will be. Okay, so that is my solution, and now I will be thinking what should I my predictions. So this is my computational domain. If I say that this is adiabatic, this theta is non-dimensional sense is 1, and on the right hand side is Tc upon Th is the non-dimensional temperature. This is what the computational domain is. Now, what are the governing equations? Governing equations continue to, this momentum, you see, in the momentum, y momentum equation, second part of it, g beta delta t. What is that term? Can anybody say? G into 1 minus beta, that is the buoyancy term. Because of the temperature difference, that's the buoyancy term, it's coming up. Now you go to energy equation, what you will see. And what we are targeting for? We are targeting that if your momentum equation needs to be solved and energy equation needs to be solved. And when momentum equation is solved, what you are going to get? Yes? Velocity field. And when energy equation is solved, what you are going to get? Temperature field, right? Now you think of, when you are solving that velocity or momentum equation, what you need? Temperature. Unless you have a temperature, distribution is not known, you cannot solve the velocity field. Similarly, you come to the energy equation. You are having uv. Means, if u and v are given, then only you can solve the temperature field. There lies the actually clumsiness. There lies the complexity. Means, you cannot, if the momentum equation, this temperature term would not have been there, then you could have directly solved. Similarly, in the energy equation, this u and v would not have been there. You could have solved the temperature field. But here, they are coupled. One equation is not solved unless other one is solved. So both have to be, how to solve that? Then you have to, while solving the momentum equation, you have to guess the temperature field. You have to guess the temperature field. And based on that guess temperature field, you have to solve the momentum, means uv, velocity field, you have to find it out. After knowing the velocity field, put that velocity field in the energy equation, get that of your temperature field. You have guessed temperature field early. Now you got that of your, based on that, you got velocity field. Based on that velocity field, again you got the temperature field. If your guessing is correct, then this will match, else there will be difference. So till that difference becomes 0, you go on adding and adding, and ultimately this iteration continues, and you will be coming to solve both the momentum and that of a energy equation, landing or giving you that of a velocity field and temperature field. This is what is the normal process what you used to do. For that, finite difference, finite volume, finite element, all these models you are supposed to be taken over. Now, here it is what happens. We used to take some of the assumptions initially to start and to go for scale analysis. What is scaling analysis? Scaling analysis is before, because the physics is not known, how it will behave, what will be the flow field, that's not known to me. Absolutely, I am starting the job. How to know that? Now, the first approach should be the scaling analysis. Scaling analysis means within a very small intellectual effort, you can understand some of its physics from this analysis. What is this? In which direction it is dominant? That we need to only understand. So that is one, I am just giving you this. So what happens immediately after t is equals to 0, just when we start, t is equals to 0 means time. We are saying both fields are temperature, were the same temperature, all of a sudden we have raised the temperature of the left one. So at t equals to 0, what happens? There was no movement in the fluid, because there was no temperature gradient at t equals to 0. So what happens? So under that condition you can think of what happens, you see, UV, energy equation where now you go at temperature T equals to 0, what will be the value of U and V? There is no flow field, so therefore U and V equals to 0. So now if you put it in energy equation, U and V equals to 0, so ultimately this inertia term delta T upon time is balanced by that of your alpha delta square T upon x square. Now question comes, out of these two terms, delta upon del x and delta upon del y, which one is more important? You have to think of. Del upon? Yes, come on. Del x. Because del x term is the boundary layer, right? So which is very small. 1 upon very small is a big quantity. So that is more important compared to that of a del upon del y. So here you can neglect this delta t, del square T upon del y square in comparison to that of your del square upon del x square. So now a complex math has been reduced and gets simplified, and based on this small approximation u and v neglecting at the t equals to 0, what happens? That inertia delta t upon t becomes alpha delta t upon small delta t square, means boundary layer thickness you are getting an effect. What is immediately within no time, just within whatever 1 or 2 minutes, I got an information that what should be the boundary layer thickness, and the application is alpha t to the power 0.5. As time progresses, this boundary layer thickness increases. That is a beautiful physics we are getting just by adjusting which term is important and dominant. This is first approach we used to do, and this continues, right? I will not touch this, I am just saying how we used to do. So similarly, inertia term, viscous term, buoyant force, there is a competition between them. Ultimately, we are non-analyzing them, 1 upon Prandtl number 1 and this. So when Prandtl number is higher, left hand side term goes out, and you are landing with something, what should be the velocity v component which you are getting over here, and I am just taking, as time progresses, inertia term also goes out, and ultimately convection versus conduction, there is a competition, and we are ultimately reaching to what should be that of your Nusselt number as a function of Rayleigh number, right? So these are, means while going this total analysis, a small thing what I just showed is that how quickly we will understand the physics of it. Physics of it means what we say, in what time frame which force is important, right? And once we know that, ultimately we are saying what are the controlling parameters. What are this? Nusselt number happens to be the output, how much of heat will be transferred. What is the input? Here it is saying Rayleigh number. What's the Rayleigh number is all about? Rayleigh number is nothing but talking that of a force because of the temperature gradient, because of the buoyancy force, and it is within an enclosure. We are talking of the height of the enclosure and that of a fluid it is handling. So altogether it's a combined effect of that of your buoyancy, enclosure and that of a fluid. Together we are talking of Rayleigh number, which is the input, and output is your Nusselt number. And you see, it is not an equation form, it is saying proportional to this. Now the target, our objective is to make it an equation form. What is the equation form? Nusselt will be k times of Rayleigh number to the power something, right? So that k, how to get it? You have to do some of the experiments or some of the analytic or whatever way, the other way around, you have to find out that k value. So here, my point is, within 5 minutes, we are able to understand that what are the physics, how this, which force is playing the important role, whether delta by del x is important or del by del y is important, at what time frame, what is frame, how boundary layer grows with respect to time. So just a mere, may not be accurate, but it gives an idea. So which lands ultimately, what is input parameter? Rayleigh is the input and output is my Nusselt number, and my target is what? It should be appearing as a equation form. So in order to get that k term, I have to conduct something else. But I understand that Nusselt happens to be a function of Rayleigh number in case of what? Natural convection within a differential cavity. Okay? So taking that k value, we used to do some that of your experimentation. Here we say that of your natural convection so that we can augment, and here just we have developed in IIT Bhubaneswar, we do have a laser source, and on one side is a differential cavity, another is a compensating cell. Ultimately we are capturing the image of the field, temperature field, by the through CCD camera and through computer. We are having that, and the point here, the philosophy is, we are giving this rectangular path. You start from point A to end point, so both way you go. So this is A plus B, and here it is also C plus D. Because of a rectangle, you go the same path one corner to the other corner. The path remains same, but path length is different because one side is heated, another side is not heated. One side the heated means it's that of a temperature is changed, temperature field is changed, whereas compensating chamber we have not changed any temperature field, so we kept as it is the normal temperature. Therefore, comparing to the compensating chamber, temperature is higher, density is different, refractive index is different, the optical path, therefore they are different, and optical path length is a indicator of that of your refractive index, and refractive index is an indicator of density variation. Density variation happens to be an indicator of the temperature variation. So ultimately it will give us that of your temperature field. So this is what we used to do, that of your experimentation, and these are some of the results we used to go. These are the fringes when it is a conductive domain. This is the thing, and if it is a convection is going on set, so this is whatever the phenomena we are getting. Rayleigh number 10 to the power 5, aspect ratio. These I will be showing some things after this numerical also. Now coming back, this is what is the experimental observations. Now what we go for numerical things, that is your governing equations in a vorticity transport equation. This is momentum equation appears like this, energy equation is looking like this, and we need to solve it. After solving, so this is the results we are getting. RC is equal to 0, where we say that no radiation is considered, and you see these isotherms are perpendicular to the adiabatic walls. Isotherms are perpendicular to adiabatic walls means temperatures are same, therefore delta T becomes 0, Q equals to 0. So this is what one of the check. The moment you get some numerical result, don't allow as it is, you have to check whether they are as per your boundary condition or not. So when now this is perpendicular to the adiabatic wall, it indicates the boundary condition of adiabatic condition is obeyed. And the other part, what you see the left hand side, that of it is quite clumsy, the middle one. You will see that the intensity of the isotherms are quite high compared to the upper portion. What does it mean? It means, yes, anybody? Isotherms when it is somewhat, yes, anybody can say? Yes, pardon? Temperature, here you see. So here, this is the portion. This is the portion where you see that of your isotherms are very close to each other. On the top of it, it is not. What does it mean? It means that is heat flux in the lower portion is quite higher because here delta T upon del X. Delta T upon del X is higher over there. So heat transfer at the lower portion of it is quite high compared to the upper portion. Now when you want to apply, for example, your PCB, computer cabinet, and you want to put your, that should be, it should be lost. Where it should be put, either in the top portion or the lower portion? Obviously lower portion, because heat will be carried away from that. So this is what the indicator of what should be the location of this. Okay, so what we wanted to say through this isotherms diagram, which part of the well is more sensitive. Once you know that affair, oh, this part is sensitive, this is insensitive, then you can decide how your design part of it. That is what I wanted to say, and it is followed by your this vector plot speaking about the flow field. Higher the flow field flow strength is there, you will say that heat is transferred very effectively. When it is quiescent, little bit stagnant, then it is air. When it is stagnant, what happens? It is behaving as an insulator, right? So when it is moving, it is carrying over the energy and dumping on the other side. So that's more effective. So obviously, higher is the Rayleigh number. You will find that if you see the next one. So you see this portion, Rayleigh 10 to the power 6. Further, it is intensified, right? And you see this flow strength is again quite vigorous. Middle portion becomes stagnant. Means it is behaving as a jet and moving around it. You just compared with this and this, you can understand. Here it is, throughout that domain, very small flow field is there. But as you go on, you see there is a completely jet is moving around, and middle, because of its inertia, middle portion becomes stagnant. But this portion, which is taking away the heat from the well, it is very strong. So that is an indicator of that effective heat transfer from the well, right? So this is how we used to do an indicator. Similarly, we have seen that if in experimental that of your outcome, when Rayleigh number increases, your also intensity that also goes on. So this is what, if it is something tilted, and if your hot wall is on the top and cold wall is the bottom, what will happen? Hot wall is on the top and cold wall is the bottom. What will happen? No movement, no buoyancy. So therefore, this is an indicator, there is no buoyancy, no convection, and you can understand that your code is working properly. Otherwise, how to test whether your code is working or not. Okay? So this is what is one of that. Now I am adding on that of a radiation. So that convection is one part, and if radiation is very pertinent to combustion, so if we add that of a radiation, what happens, how it is getting affected. That is what is basic objective. The radiation itself, you know how this radiation is different from that of your conduction and convection. Conduction and convection happens to be a local phenomena, whereas that of your, this is a global one, long range phenomena. And when that of your conduction and convection both do coexist, and it is always existing, there is no doubt about it, and only because we used to, at the time of simulating or the time of modeling, we are not considering, oh, this radiation is negligible. Means we are I mean saying this is, we are not considering, but in reality, that is always it is there, whether it is a, I mean some substantial form or not, that is different, but always it is there. So now you see it is a short range phenomena, that's conduction and convection, whereas that if a radiation happens to be a long range phenomena, mean free path is 10 to the power 10 minus, whereas mean free path is minus 10 to 10 to the power 10. We are getting that if you are from Shan to over here, means so long. So means, what does it mean? Whenever there is a radiation, what will happen? You have to take from 10 to the power minus 10 meter to 10 to the power 10 meter. Whereas if it is a conduction and convection, you are now handling 10 to the power minus 10. Means it's a local one, local phenomenon. But here it is a long range phenomenon. How to put it into math? Because finally we have to solve in the mathematical form. So what mathematics will be, how mathematics will represent both conduction and convection and radiation. That's the point. So I'm just coming. So this will be obviously, you see last part, it leads to an integral equation. What? Radiation. And whereas conduction and convection, they lead to a partial differential equation. We just discussed about partial differential equation, and whereas when radiation is there, it is an integration because 10 to the power minus 2, 10 to the power 10. So obviously some integration effect is to be there. So this is all you understood, what's the radiation and conduction, how they do differ, and this is the application of purely radiation. And here, friends, radiation we are categorizing into two things. One is that of a surface radiation and that of a medium radiation. Surface radiation, when I say that air is the medium and it is dry, dry means no water vapor is there, then I can consider the air is a transmitting medium and only walls will be radiating and air itself is not participating. But in combustion phenomena, what happens? CO2 will be present, CO will be there and H2O will be there. So this medium is no more behaving as a just a transferring medium. So it will be a participating medium. So each point there will be some photons will be coming and some photons will be absorbed, some photons will be scattered. What is the photon? Photon means the representation of the radiation which are nothing but the carrier of the energy. Okay. So these photons we call in a term radiation intensity. Radiation intensity talks about that of your photon, mathematics, photon arithmetic. So this is friend, this leads to, and these are some of the things you see after absorption what happens, radiation comes down, obviously number of photons gets absorbed, 10 units, 10 photons have come within a medium, 5 are being getting absorbed, so leaving will be 5. So this is a very simple understanding. So that is coming as, you see In equal to 0 to e to the exponential variation of this. These are the some of the laws. Similarly, scattering. When it comes in this direction and get deviated in another direction, not going the targeted direction, we call it that is scattered. This, as a matter of fact, is coming this type of equations. So you see, what happens? Left hand side is taking what should be the intensity variation. Intensity means what is the number of photons they are coming and how photons are leaving. So what is, we do have a domain like this, number of photons are coming from one direction and we are going at the end of it, how many photons are going? So between incoming and outgoing, what happens? What are the phenomena? One is they get absorbed by that of a domain under consideration. Some part I have shown you, they're scattered. Once it is scattered, we are not considering in the same direction. Therefore, they becomes negative. Okay, absorbed also negative. So these two terms, absorbed and scattered, they will be considered as the negative things. Now, who augments? Augments if the medium itself is emitting, then we will say that that is radiation is augmented or strengthened. The other part is from other direction some radiation are coming and joining this direction, then that is also additional. So therefore you see there are two minus terms on the right hand side. One is scattering then next term is absorption. These two are negative. The next one is epsilon IB, that medium itself is emitting. Then this integration means in scattered portion, means it comes from different directions and 360 degree, we call it in scattered, that becomes a positive. So two positive terms and with two negative terms is giving you that affair. What happens to that affair? Photons. Why we are talking of photons? Because photons are the carrier of the energy, and we are going to solve the energy equation. Energy equation will give us what? The temperature, right? That is what is the target. So unless you solve that affair, radiation field, you cannot find out that affair temperature. That is the crux of the thing. That is the summary. So we have to have that affair. You have to solve the radiation energy equation. This is what we call it, radiation transport equation. So these are some, I am not taking you to much of math. So here it is spherical harmonics. Here we are trying this model and landing with the irradiation term, where it is converting that affair, that is integral differential equation, into a partial differential equation where del square g upon del x square, del square g upon del y square, something c into this. So that partial differential equation it becomes, because you are comfortable with the partial differential equation. So this is one model, what we call it, spherical harmonics method, where integral differential equation is now converted into that of a partial differential equation, because we are very comfortable in solving partial differential equation. Therefore, this is the way or approach. The next one is discrete ordinate method, another model where we say that this integration which we are talking, in particular direction we will assign some of the weights, so that you can, this integrating effect will be assigned with the respective weights, and we can summarize, we can quantify what is the radiation energy in a particular direction. That is what the philosophy of discrete ordinate, ordinate means direction, and in the particular direction, what is how to prescribe or ascribe some of the weights so that radiation energy can be quantified. So this is how some of the methods I myself developed in 2005, I remember. So that is a hybrid method, which is a combination of the spherical as well as discrete ordinate method, and which has come to a very nice outcome. And because this is an optimized, they have their own limitations, because spherical has a discrete ordinate method having a optical thin, whereas spherical harmonics method is optical thick. So I personally developed a combination of these two, what we call it hybrid method, and this is ultimately our target is to quantify that of your radiation energy, and radiation energy, unless you are quantifying, you cannot gauge that of a temperature field. Okay, this is what is the objective. So taking into this, you come to that energy equation. Energy equation means, here is the term. Earlier this was the term only convection. Now this is the term which has been added because of the radiation. What is this? Del dot QR. This is del dot QR means you have to, divergence of the radiative heat flux you have to quantify. If you know that, then your theta you can evaluate. Theta means temperature of the temperature field of the domain you can evaluate. Otherwise not. So our target, therefore, this del dot QR has to be evaluated. How it will be solved? It is to be solved using that of your radiative transport equation, which I have given you just 2-3 models, and these 3 models can help you to find out gradient of the radiative flux. Once radiative flux is known, then temperature field will be known, and velocity field, all these things club together. Now you can understand. So friends, these are all methodology. Hybrid method I have highlighted because these two combinations effects have been combined in the hybrid method, and just now I have shown you what is a distinct function. Numerical schemes, we have taken some finite difference, finite volume. Now this is the, when natural convection and radiation together they do exist, how the flow profiles are looking. What is the difference, if you remember? Here is the difference. Here is the difference. You see, earlier it was normal to this. Now this has been inclined to that. What does it mean? Delta t upon del y is no more 0. Delta t, earlier delta t upon del y was 0 in presence of natural convection. But when the radiation is present, because delta t upon del y is k into delta t upon del y plus qr together is 0. But individually is not 0. That's the point. So delta t upon del y is equals to minus of some qr radiative component. So therefore that's not 0. So this is an indicator that here it is some radiation component, the field is radiation, effect of radiation is already same. So this is how the situation is. And even if an experiment, we have conducted one trapezoidal enclosure with a fin, and numerically what we did, we just did some natural convection and we took the fringe. Then because in the experimentation radiation is a part of the phenomena, but it didn't match. Then natural convection with that of your interferogram which you got from the experimentation. What then? Why we said no, so air was the medium. So it was only that of your surface radiation is a part of it. So we just, what we did, just we went ahead of changing the emissivity. As a matter of fact, emissivity at a 0.85, we see that this is matching nicely. Okay, so this gives an information or inference we can conclude. Radiation is a part of, it was there. In numerical solution you didn't consider it. Therefore it didn't match. Then when you consider that of a surface radiation as 0.85, emissivity as a 0.85, now it more or less matches. So this thing we used to do just to say that yes, radiation is a player, don't miss it, and you will be losing, that is in predicting things. So another thing I have already, we did it, one of my students did it, is a doctoral student, is a mixed convection and radiation. Mixed convection means is a forced convection and natural convection together. So what happens? In case of your combustion chambers, blowers have been provided. Convection by default temperature is there. So radiation will be part of it. Plus that of it, when free convection is inherently it is there, and forced convection because of the external agency that will be there. So therefore we took it as a mixed convection and also radiation together for modeling purpose. So here it is. What happens? Theta is equal to left hand side is theta equals to 1 and right hand side this is. So natural convection is this is the length, and when I just put this way, these two plates are moving. So what happens? This is a forced one. This moment is a forced one. This gives an opposite motion. This natural convection is this way, and that of your, this because of this moment, plate moment, this gives an opposite motion. So this is what we call it opposing convection over here. And when it is moving in this direction, this is heading. Whatever the natural direction, also forced convection is same direction. Therefore we call it, this is heading direction. Okay. So obviously you can guess it in which convection the heat transfer will be more. Heading convection it will be more, and we also got the same thing. And opposing convection we also got some of the reduced values. But how much it is, unless you do some numerical, you cannot get it. So we did it, and which has been published long back. So this is, I am not showing heading convection, this is what opposing convection result is like this. What you see when this is the situation, you see this is the flow, I mean these two plates are moving like this. As a result of which forced convection along this direction, natural convection is this, so this becomes your opposing convection. So opposing convection, you see, what is the Array, do you know? Array is a Richardson number. Richardson number speaks about that of your competition between Reynolds and that of your Rayleigh or Grashof number. Okay, so Grashof is talking about the buoyancy and Reynolds is talking about the forced. So if they are of the same order, means same order of magnitude you can say. Means both forced convection and natural convection of the same order. But they are now opposing. Once they are opposing, what happens? The flow, you see the cell. Now we do have 3 cells. 3 cells means when your resistance you put it, they are in the circuit. 1, 2, 3. What happens? This is the hot wall, this is the cold wall. When resistance are in series, what happens to resistance? Increases or decreases? Increases, right? Once the resistance to the flow increases, what happens? Heat transfer, it comes down. So this is how we understand from that of a cell structure. But the cell is the outcome, whatever you see, that of your CFD results, right? Whatever the governing equation we sort, and that of outcome is like this. So you see here, same phenomena, Richardson number 1, what happens here? RC is equal to 10. What is RC? RC is nothing but radiation conversion parameter, means radiation is present here. The earlier one, the radiation was not there. Now I have intentionally put that what happens when radiation is present and Richardson number is 1, means forced convection and natural convection of the same order of magnitude, and both are opposing in character. So once what you see, the middle cell vanished. The middle cell which I have shown you earlier, that is no more acting. So what is the inference now? Inference is, in presence of the radiation, the middle cell is no more working. It is going out. So then why a cell is formed? Cell is formed because of the local temperature gradient. When local temperature gradient is existing, so fluid will be flowing from higher the temperature, lower will be the density, and the fluid will be going out, creating a vacuum. So therefore the adjacent fluid which will be coming to that. So when temperature gradient will be there, so naturally flow will be occurring. So now the question is, when the middle one, when the middle phenomenon was there, some local gradient was there, now in presence of the radiation, this gets homogenized. Radiation, what it makes? That of you try to make that of a phenomenon temperature to be homogenized. So as temperature is getting homogenized, so gradient which was existing, that is completely lost. So as it is going out, so this middle cell is going out. So this is what is the man's finding, and this is the effect of the radiation, what I am saying. Similarly, over here, you see this is radiation conduction parameter. You see 100. 100 means altogether, totally, there is no temperature gradient. So means this is the domain. If radiation is too much, you can't see that. If there is in between anything happens, it's just a quiescent phenomena, and radiation makes that appear homogenization. Means there is no local temperature gradient, and local temperature gradient, as a matter of fact, is creating that appear flow to happen, flow to occur. So this is the other configuration I have shown you. You see, this is what Ri 2.5, similar cells. This is horizontal one, okay, this moment, and this is the higher temperature and lower temperature, and this is the moment. So this is 3 cells you are getting, and coming down, this also, you see, it goes out. This almost, you see, in between it goes out. So this middle cell now, it is lost. Same thing we will see whether it is these 2 plates are moving or these 2 plates are moving. Same, physics remains same, physics cannot be changed. So when you conduct the same thing and ultimately landed with this, it is become easier to come with the what is the physics. What happens? Natural convection is affected by radiation, whereas that forced convection is not getting affected. So that's the whole thing. Which one is the natural convection part? This is the middle cell was because of the contribution of the natural convection. Now in presence of the radiation, that goes out. So that's the what we can conclude from these observations. So my friends, these are some of the conclusions. Discrete ordinate method and hybrid methods and their applicability we have seen that they are for optical thick, and discrete ordinate is meant for optical thin, whereas spherical harmonic is meant for optical thick, and hybrid model I have developed is moderately optical thick medium. However, it is time consuming For buoyancy aiding flow, flow circulation in the cavity is quite strong. The term pure convection is applicable for Ri equals to 1. Ri equals to 1 means that of a Richardson number, Richardson number is 1, where Reynolds and that of your Rayleigh is the same order of magnitude. And multicellular flow, I have shown you 3 cells like that. So in multicellular flow, and you see radiation has a little effect on forced convection. It has a strong effect on natural convection, which I already explained you. Okay. Radiation causes flow reversal across the mid of the cavity. So radiation, as a matter of fact, flow reversal in the cavity also it makes. So that is what essence of understanding radiation. And radiation is a part of the combustion. We just can't avoid it. And this is, without that, you cannot think of that of a, you can really, predict something about that of a combustion. And influence of radiation in mixed convection is more sensitive for buoyancy opposing flow than buoyancy aiding flow, obviously, because that's the situation. So some of the journals we used to go for that, so that whatever we are saying, that is internationally it should be accepted. And this is all CFD code, you understand. The users must have the skills and experience with the number of areas, problems of identification and combinations, and genuine assumptions to make equations simplified, whether to model with 2-3 equations to or 2-3 dimensions, all these things. And we used to conduct some of the grid independence test, assessment of the physics of the solution, experience is needed. At the end of it, that if your numerical solution and experimental solution, they should speak the same thing, then only we can come to certain inference. Otherwise it is immature to come without to state some of the thing. That is only when then those things can be transferred to technology front and go to industry platform. And this is last slide is important. Thank you. Okay. And some other things, similarly other domains we have done it. And here it is the last line you can see. This is again in a cylindrical domain. This is the effect of the radiation. So altogether it's not there. But if it is radiation, that is something is coming up. So radiation is, whether it is a cylindrical or that of a cavity or a furnace, whatever, radiation has its own role to play. And similarly, some of the open cavity problems we also did, and just here from the Magander, from the flow infogram, we can say that because air is flowing through the door, I'm not able to sense it, smell it. So if I do have a Magander over here, I can understand how much mass is entering. That is what the open cavity phenomena, just one of the scholars, they have done it. And at the end of it, your combustion will be requiring, in addition to energy equation, some of the species transport equation, which is still complex. And that's why Professor Sau was talking about that if some of the softwares, people come up and the background of the software, whatever I have shown you. And this is how you have to come up the codes, and the results have to come up, and then it goes to that software platform, because software cannot handle a very small cavity or a rectangular domain, and real thing is altogether different. So it is to be done. But the physics, whatever you want to explore or extract, this is the beautiful way you need to realize yourself and to understand the physics of it. So you see some of the numbers like Lewis, Surrey and Duffer, I don't want to. This is the domain of Dr. Sahu. I'll be again, thank you once again for your presence here. Thank you. Any other questions? On that. Any question, anything? For me also difficult to answer, I know. But yes, anything else? So this is what normally is to be done, and if you can take it up, that makes sense, because this particular background will help you to develop some of the softwares also in your area. This is how, before developing a software, this is your own knowledge, because whatever you are numerically developing, experimental establishing, both should stick together. Then thereafter come with that as a concept and say that. For example, the concept is natural convection is affected by radiation or forced convection is affected by radiation. So answer may be coming out. Both mean what radiation is radiation affecting the same. But what we saw that if a natural convection is affected. How can you say like this? Only when you see that of your experimental and as well as that of your numerical. So these things you have to come up after having those investigations. Okay, once again thank you.